Okay, welcome back. So now we'll look at some of the shift and rotate instructions from chapter 7. And the idea with starting with the shifting instructions is that we can shift in both directions. So we can shift in the left direction and we can also shift in the right direction. But one question that comes up is, because you actually thought about this concept several assignments back, right? When you had to do things like shift the lower half of bits from EAX to the upper half, but you did it through several different add instructions, like, add EAX, for example, 16 times. But now we'll look at the actual shift and the shift and rotate instructions, so we do have the ability to directly shift bits using those instructions. But when you think about the issue of shifting bits in either the left direction or the right direction, we have to think about a couple of things. Because, for example, we might have a binary number like this. We might have a binary number like that, right? And maybe we want to shift that whole number, so in this case, an 8-bit number, 1-bit position to the left, meaning all of the bits will get shifted to the left. And so we'll talk about what happens to the bit that gets shifted out. But also something new is going to have to come in, right? Because the number itself is still going to be an 8-bit number after we perform the shift. So if we want to shift it in the left direction 1 bit, then in particular, we're going to lose, right? We're going to lose this bit. Because that's exactly what we mean. If we're shifting all the bits to the left, right, meaning this way, then the uppermost bit, the MSB bit, right, is going to be pushed out of the number itself. And actually, as we'll see, it's going to be placed into the carry flag when that happens. But at the same time, to keep the number still 8 bits, something is going to have to be pushed into the low end, right, the LSB end. And it turns out, right, that that's going to be a 0. So when we push in the left, or when we shift in the left direction, the new bit that we bring in at the low end, meaning the LSB end, is always going to be a 0, with at least with these initial shift instructions that we'll look at. So, and we'll talk about the different combinations of shift instructions here. But the first instruction that we'll look at here is SHL, which means shift left. And we'll eventually talk about SAL and then their counterparts, SHR and SAR. So we can shift in both the left direction and the right direction. And furthermore, the issue of what's called a logical shift versus a arithmetic shift comes up. Although we'll see that that issue really comes up when you're shifting in the right direction, not really so much when you're shifting in the left direction. Question? If and we should. Well, yeah, okay, good question. If no, so although you could do it, you could potentially do a shift with something like AX, for example. But if you're doing like a shift instruction with AL, then you're only shifting an AL, in other words. So just like these other instructions like move and add and sub and so on and so forth, when you work off of a lower level, like an 8-bit level, right, it does not carry over into the rest of the register. Because it's important, you know, if we're using AL as our operand, then it's important that it doesn't start to carry over into AH. So similar to other instructions, if we do like a shift left with AL, then that's, in terms of registers, right, that's only going to affect AL. It's not going to, for example, carry over into the AH part of EAX. So the only way that it, you know, that both would be affected is if you did like a shift over AX. But it is going to also involve the carry flag, because that's where it turns out the MSB bit in this case would be placed. So what we're saying here is if we start with this 8-bit number, and maybe it's an AL, for example, then what's going to happen is this one, meaning the one that's shown in red, is going to now be placed into the carry flag, right, CF. The other 7 bits are going to all move up one position, right? So for example, this one is now going to become, meaning the one that's highlighted right now, we'll put that in a different color, but that's going to become, let me switch here for a minute to fix the screen share. But that second one is going to become the new MSB. Right, the one that's now in green, right? That's going to become the new MSB and the new 8-bit number that we get when we shift it. So all the bits move up one position, in this case to the left, since we're talking about going in the left direction. The new lowest bit is going to be a 0, assuming we do one of these two instructions, SHL or SAL. And then that original MSB, the one that's in red there, would be in the carry flag. So we'll just say if AL equals this 8-bit binary number, so that's a binary number, and then we do, and the instruction here that we'll do for now is SHL AL, 1. So the name of the instruction is SHL, shift left. The thing that we're wanting to shift is AL. The second argument is the number of bit positions that we would like to shift. So it is possible to, in one instruction, right, do multiple bit positions, but that's the equivalent of doing one bit position several times, right? But we can do that as well. But here to start, we'll just do one at a time for now. But shift left AL1. So the second argument here is either a literal value treated as a bite-sized value, or CL can also be the second argument, but it's one of those two things for the shift amount. But we're going to go ahead and shift it to the left 1-bit position. So then taking it all together here, right, CF is going to equal to that, you know, the one that was in red here. AL is going to be, right, those bits. And then a new 0 at the end. So that again, so like that, right? Carry flag, again, carry flag in this case is storing this one. The other 7 bits are all still in AL, right? They all got shifted up one position to the left. And then the new LSB, the new bit that was shifted in, was a 0, which we put in blue here. So that's going to be the result of what happens if we do a shift left AL with 1. So in other words, when you shift in the left direction, the carry flag is also the leftmost part of that shift, meaning that the old MSB from the operand, in this case AL, gets placed into the carry flag. So now carry flag has 1. So the idea also is that as a result of this is, you can parse the individual bits within a number as well, because for example, if you shift them, each time you shift 1 by 1, the numbers will end up in the carry flag. And then we know from chapter 6 that we have jump instructions, right? Including jump instructions based on the carry flag. So, it also opens up the possibility of doing things like, checking each bit in the number in the operand, and then doing one thing if the bit is a 1, maybe doing something else if the bit is a 0, because we know that each shift is going to affect the carry flag. And we have jump instructions like JC, jump if carry, and JNC, jump if not carry, that can jump directly based on the value of the carry flag. So that's another thing that comes up here as well, is that we can, in part use shifting algorithms to maybe analyze, for example, the individual bits within the operand, and then make a decision based on whether the bit, the current bit is a 1 or a 0, combining this with things from chapter 6. But that's the basic idea. We'll also see that when you, as a consequence of doing this, right, whenever you shift in the left direction, you're also really multiplying, by powers of 2. And we'll see that when we look at some examples, but since we're taking all the bits and shifting to the left, right, all the bits are moving up 1 bit position. So that also has the effect of doing some basic multiplication, at least in terms of powers of 2. So for example, if you take your number, however big it is, and you shift all the bits to the left, then you're multiplying it by 2. If you do that one time, if you do it again, then you're multiplying by 4 or by 8, and so on and so forth. Conversely, right, it follows that if you go in the opposite direction, the right direction, then you're also dividing, right, by powers of 2. So if you take all your bits and then shift them in the right one direction, you're dividing by 2. If you do it again, dividing by 4, dividing by 8, and so on and so forth. So it also does mean that, we can do some, at least some basic anyways, multiplication and division with the shift instructions. Now there are multiply and division instructions, because for example, when if you shift in the right direction, you can get the quotient part of integer division, but you're not going to get things like the remainder. So that's why we still ultimately have multiply and division type instructions, but it also does mean that you can do some basic multiplication by powers of 2 or division by powers of 2 with things like a left shift or a right shift, because of the way that it works. And again, you can also, if you get a little bit creative, you can also try to handle things like maybe multiplying by a number that's not a power of 2, but you'll have to do more than just the shift in and of itself. But that's another, utility or use of the shift instructions, is we can do some basic multiplication or some basic division, right, by shifting in either the left direction or the right direction, because we know that if you take all the bits and you move them up to the left one, you're multiplying it by 2, right, each time you do that, right? Or conversely, if you take all your bits and move them to the right one position, then you're dividing by 2 or by more than 2 if you do it multiple times. So that's another thing too, is that we can do some basic basic multiplication and division using things like the shift instructions to help out with that. Again, another utility is we can take advantage of the fact that the carry flag itself is involved in this whole process of shifting. And since it follows that each bit, when you shift it, moves into the carry flag, in this case, if we're going the left direction, it's the MSB bit, right? Then you can look at the carry flag and make decisions based on whether the number that you just, whether the bit that you just shifted out, whether that was a 1 or 0, by combining this with things from chapter 6, like the JC and or perhaps JNC instructions, depending upon what we want to do. But so that's the basic idea of a left shift, right? So everything's going in the left direction. And then there's a good graphic also here kind of showing the basic idea with some of the slides here, but in terms of how you can in general think about a left shift. But what we're really doing is this kind of thing. So whenever you're going in the left direction, just remember that it's the carry flag that's the leftmost thing, right, in the shift. So MSB bit is going into the carry flag, all the bits shift to the left, and then we bring a 0 into the low end. And now there's also the instruction SAL, which means, the A means arithmetic. So we'll see that there's a difference with the right direction anyways, with a logical shift and an arithmetic shift. But SHL and SAL both really do the same thing. In particular, both are going to shift all the bits in the operand one position to the left. Both are going to take the old MSB bit and move that in the carry flag, and both are going to bring a 0 in as the low bit. So what that means is that a logical shift, which is what SHL is, and an arithmetic shift, which is what SAL is, they do the same thing if you're going in the left direction. But as we'll see, there's a difference between the two if you're going in the right direction. But again, left direction, SHL, which shift left, but that really means logical left shift, is the same, right, as SAL, meaning arithmetic left shift. So arithmetic and logical are both the same if you're going in the left, right, the left direction. So this diagram also applies then to SAL as well. So that's the general idea. Now, when you're going in the right direction, and again, we know that going in the left is how you can handle some, to an extent, right, some multiplication, and going in the right is how you can handle some division. But another difference also that comes up when you're going in the right direction is now everything is the other way around. Because now all the bits are shifting down to the right, which means the new bit that you're bringing in is on the MSB side rather than the LSB side. And so then there's the whole issue of preserving the sign or not preserving the original sign. So just as we have SHL and SAL, we also have likewise SHR and SAR. So SHR is shift right, but it also is really logical right shift. And the idea is that with the logical right shift, you're going to always bring in a 0 as the new bit to the MSB when you shift all your bits down to the right. And also with the right shift, the carry flag is now, if you think about the diagram, right, it's going to be like this now. So this would be the diagram for something like the SHR instruction. Notice now, though, the difference is the carry flag is on the rightmost part of the diagram. So meaning the LSB is going to get shifted out this time and moved into the carry flag. And then the 0 is moved in as the new MSB value. So with the SHR, or logical right shift, you always will shift in a 0, meaning that if you think about things from a sign standpoint, for example, if we're interpreting it as a signed number and the original MSB is a 1, then that means that the sign is not preserved, right? Because of course you're gonna push in a 0, and then from a sign standpoint, it's no longer going to be, right, a negative number because it has a 0 now in the MSB. So SHR again does not preserve sign, right? It just pushes in a 0 always. So with things like trying to do some basic division, of course, that means if we're interpreting it as a negative number, then the result would not be correct if we're interpreting the data that way, because your original number would have a 1, for example, in the MSB, and then when you do a right shift, you'd have a 0. And so it's not going to be correct, right, from that standpoint, at least. So there's times where we might want to do that. So you can think about things like, unsigned, right? If we're just treating the data as unsigned, then we might want to do that, right? Because then with SHR, you'd always be pushing in a 0, which is fine. But especially if we're dealing with things that are being treated as signed data, we may not want to just always push in a 0, right? We might want to actually take into account the actual value of the MSB as far as determining what you're going to shift in. And so that's where SAR, the arithmetic right shift, comes into play. So SHR always will shift in a 0 to the MSB, but SAR, the arithmetic right shift, will take into account the value of the MSB. So this diagram here models what happens with SHR, and then this diagram here models what happens with SAR. But notice the difference. Notice the difference in the two diagrams. So with the logical right shift, it's a 0 that's always brought in as the new MSB, and then all the other bits shift down, and the lowest one goes in the carry flag. But notice here in the diagram, you have that, and that MSB bit, it goes back to itself, right? That arrow goes back to itself. Because if the MSB, for example, is a 1, then you're going to shift in a 1. If the MSB is a 0, then you're going to shift in a 0. So either way, with the arithmetic shift, the sign is going to be kept the same, right? If the MSB has a 0, then it's always, right, going to have a 0. So in that sense, right, it'd be similar to SHR because you'd be pushing in 0s. But if the MSB originally has a 1, then you're going to always push in 1s as the new bits. So from a sign standpoint, positive numbers will always remain, right, would always remain positive numbers. And then negative numbers would always remain negative numbers because the sign stays the same. Yeah, good question. So SHR, especially with unsigned, certainly has its uses. Because, I mean, you could be really anything could come up here. I mean, you could have data that's unsigned or that we're saying is unsigned. The CPU handles everything, the same. So it's up to us to interpret it correctly. But you could even have, something that's intended to be thought of as unsigned and have, for example, a 1, in the MSB, but since it's unsigned, we would still say it's positive. And then, you want to do, for example, a basic division operation with that unsigned value. But if you use, SAR, then it's going to still treat it, right, as if it were being interpreted as signed data, and it would shift in a 1, to the MSB. Whereas if it's SHR, it would still just shift in a 0. So if it's unsigned, right, we don't want to, because if you think about, the difference there, um, if we're wanting to treat it as unsigned, then we don't want just ones always, being shifted in. Because if you think about just an example here with 4 bits, you could have, um, you could have something like the number 8, for example, and then you want to, if you shift it to the right, you want to get 4. Well, so with SHR, right? Again, we're just looking at, a small number example here, but you'd get like that instead of having, 2 ones for the upper 2 bits. So unsigned versus signed, right? Like with many things can come into play here. So SHR can be used certainly to do things like unsigned division with powers of 2. And then SAR can be used for signed division of powers of 2. Because, again, if we're saying this is 8, and then we would have, but with the same number, -8, have 1, 1, right, for example, and then you'd have -4. So yeah, in general, if we're wanting to do things like unsigned division, then we should always use SHR, right? Because SAR is intended to be used with a signed interpretation. Because again, this is the difference, right? Same bit sequence, but a different meaning in both cases. Unsigned, right? This would be 8. SHR, 0, 1, 0, 0, 0, or 4. Same bit sequence here is signed, so -8, and then you get -4 since you have both of the 2 upper bits are 1s. And again, that's an example with 4 bits, but of course the same idea applies to 8 bits or 16 bits or whatever. So SHR can be used for, certainly for things like unsigned division by powers of 2, and then SAR can be used for your signed divisions by powers of 2. Now here, the carry flag's on the other side, right, of the number this time. So it's on the right side of the number rather than the left side of the number. But again, similar to before, and again, we'll just work off of AL here as an example, but something like that for the original value, and then we do SHR L1, then show AL first here, and then you can show the carry flag second, since we're going in the right direction this time. So all the bits are going to be shifted to the right. If it's SHR, then a 0 is always brought in as the new MSB. And then the old LSB is going to be shifted, right? Shifted out. So that bit is going to, that 0 in red there is going to end up in the carry flag, right? We're going to shift it out into the carry flag. All the other bits are going to move down to the right. So like before, that means that this bit here is going to become the new, right? For example, LSB, right? That 0 there in green. And so again, you know, it means that we're going to have all of those bits still within the number. But that 0 now is the new LSB, and then we have a 0 at the front there, because that's what we're shifting in, right? That's the new MSB. And then the carry flag in this case is going to be that 0 that we shifted out. So at least with SHR, right, just like SHL and SAL, but just the opposite direction, and a 0 is still brought in. But SAR is where it's going to be a little bit different. Now, because we can even look at this same example here, but run it through SAR, but the difference is the bit that you would shift in, because this is a 1 originally, right? The original MSB is a 1. It means that instead of shifting in a 0 here, then the bit in blue that you shift in would be a 1, right, instead of a 0. So again, whereas SHR, you know, one usage of it is to do things like perhaps unsigned division by powers of 2. SAR could be used for things like one usage anyways could be used for signed division of powers of 2, because it preserves the sign, right? If the intention is to treat it as signed data, whereas unsigned, right, should always be used with SHR for that purpose. So some similar points here, but about SAR. So again, left direction, there's no difference, right? Because we're not talking about shifting a new bit directly into the MSB. So you always shift in a 0 from the low end going in the left direction, but certainly there's a big difference now when we talk about going in the right direction. So again, that's an arithmetic, right? And this part here is the same, shift all bits to the right, and LSB is placed in the carry flag. But the value of what gets shifted in the MSB depends upon the original sign of the number. So change this last part here. So just takes into account that. And then again, if we look at this same original number here, but with SAR, we'll see the difference. So meaning the instruction now would be, for example, SAR AL1, where we're assuming we have the same original 8-bit number. And then, but now the new MSB in blue here is going to be a 1, right, instead of a 0, but everything else will be the same. So the original 8 bits all get shifted down to the right. The old LSB in red, right, for example, goes into the carry flag. The old second to last bit becomes the new LSB, right, in green here. and then the new MSB is 1. And again, the idea is if you repeat the process, right, like if you do another SAR, you're going to still shift into 1 as the new bit, right? So the sign is always preserved no matter how many times we do it, either through repeatedly doing SAR AL1 or doing something like SAR AL5, for example, which is equivalent to doing SAR AL1 5 times, right? But we do have the ability to have a number larger than 1 here for the number of bits to shift. But if you do that, that's the same as doing it with 1 bit position that many times, right? But if we do it again, we're gonna still shift into 1. Do it again. Then starting from here, right? So this 0 would go into the carry flag. So the carry flag in that case doesn't change, right? Since it already happened to be 0. But that 0, right, is going to get shifted out into the carry flag, and then we're once again, right, we're going to shift in a new 1. So we'll group the bits like that in 2 groups of 4. So that's going to be, right, the new MSB. That'll be the new LSB. So we once again have preserved the sign. Whereas if we had used SHR, right, it just would always do 0. So again, SHR is really good for things like unsigned, right, division. And SAR, it can be used for things like signed division by powers of 2. And so that's the basic idea with these 4 instructions, right? So SHL, SAL, those 2 are the same. And then SHR, SAR, which we saw the difference between those 2. And now sometimes we may also, for example, work with data that's given, let's say, in hexadecimal. And we also might, in some cases, encounter instructions that have more than 1 as the number of bit positions to shift. But that's fine, right? We can think about how to handle those cases as well, because now when we think about things like a shift, we think of it as of course, a bit level operation, right? Because the number that we put here is the number of bit positions that we're shifting. But we also know the relationship between hexadecimal and binary. It comes down to the fact that each hexadecimal symbol is 4 binary bits. So it doesn't really matter in the end, right? Whether we give the data in hexadecimal or whether we give the data in binary, it's really going to all be the same. But nonetheless, you want to think about what that's going to look like, right? So if we, let's say, maybe now we move into, use AL here again, maybe 4F hex, for example, and then we do shift left, for example, AL1. Well, how are you going to interpret what the result of that is? Because this means rather than writing the data out directly in binary, right, we're given the data here in hexadecimal form. So AL, we're told is storing 4F as a hex value, which is also 8-bit value. And then we have the instruction shift left AL1. Well, but the thing is, right, this still means 1 bit position, right? Not 1 hexadecimal symbol, 1 bit position. So all we would have to do to try and work through this is we could just either mentally or on paper convert that hexadecimal number to binary, and then do the shift there, and then, for example, convert the result back to see what the result in hexadecimal would be. So that's the only difference if the data, right, is given in hexadecimal. So just convert that, right, 4F to an 8-bit, right, binary value, and then just work from there. Because again, you know, we can talk about things like, well, what's going to be the value of the carry flag, or what's going to be the value of the actual register, in this case AL, after doing the shift. Well, so for F, because we know how to, from chapter 1, right, the relationship between binary and hex. So 4, right, is 0, 1, 0, 0, 0, and then F is 4 1s. So we're taking that, and in this case, we're shifting it to the left, right, 1-bit position. And we said that when you're going the left direction, you can, you know, write the carry flag first, right, since that's the left, you know, most value. But in particular, we know, right, we know that this 0 is going to get shifted into the carry flag. And then all of these bits are going to be shifted down. And then since we're going in the left direction, we're going to have a 0, right, as the new bit that's shifted in at the low end. Regroup the bits here in 4s again for convenience, but then we're going to end up with that ultimately, right, is our new 8-bit number. Again, just from moving this 0, right, just like before into the carry flag. And then we have those 7 bits plus the new 0 that's brought in on the low end. And then, you know, from there, we can just convert the result back. So carry flag is 0, and then AL, right, in this case is going to be 9. And then we have, for example, E. And so that's how we can think about this process if we're given, you know, hexadecimal values to begin with. And I mean, you know, another possibility also is that we might be given an instruction that has a shift amount that's greater than 1. But that's okay too, right? Because remember, if you do that, that's equivalent to just doing it multiple times by 1-bit position each time. So, but you could have that kind of thing come up too. Say, and then because you could have, for example, something like SAR AL2, for example. So meaning in one instruction, we're saying to shift 2 bit positions to the right, and we're doing it arithmetically with SAR, where the original value is 8D hex. Well, that's okay too. So AL is originally, in this case, if we're going to have 8, then 1, 0, 0, 0, and then we have the D or 13. So we have something like that, right? But then we're saying, see, in one instruction, right? In one instruction, go 2 positions to the right. But I mean, you could also just, you know, do it step by step here too, because just do the one shift and then do the next shift and look at, you know, look at the values that you get. So after shifting once, for example, right? And since we're going in the right direction, now we'll write carry flag on the right-hand side this time. But so here, after the first shift, the first of the 2 shifts, just like we discussed before, so all the bits are going to get shifted down down to the right. The LSB is going to be pushed out of the number into the carry flag. So this one here in particular is going to be in the carry flag, and then you're going to have all the other 7 bits. We'll regroup them, of course, here. But then the new MSB, since the original number had a 1, and that makes sense also because we know that 8 in hexadecimal corresponds to a negative number in signed hex. But since we had a 1 here, right, and then we're doing SAR, the arithmetic right shift, we're going to also have a 1 that's shifted in as the new MSB. So you would have that, right, after doing it just 1 time. You'd have 1 1 0 0, 0 1 1 0. Again, since we moved that bit into carry flag, which left us with these remaining 7 bits plus the new 1 that we pushed in. So we end up with that. And then to finish this, right, we're just going to do it 1 more time because that's what we set up here, was we want to do it 2 times. But that's one way to think about it, is just to do it kind of step by step too, if you want, just do 1 bit at a time and look at all the transitions that you go through here. But so after shifting twice, just continue where we left off with the last shift, right? So now this is our starting point for the second shift, but same exact idea. So again, carry flag now is going to be set to 0 because now we're, when you look at the new state of AL, the LSB is 0. That's going to go into the carry flag. So again, down here, we'll write out both AL first, since we're going in the right direction, and then carry flag on the right-hand side. But so carry flag is going to get this 0 here, right? So carry flag is going to be 0. And then all the bits, all these 7 bits, right? It'll go there. But all those 7 bits are going to be selected here. And then we'll regroup these in 4s. And then we're going to have a new 1, right, that comes in once again at the high end, at the MSB end. So now we end up in this kind of situation. 1 1 1 0 for the first 4, right, the first hexadecimal symbol, and then 0 0 1 1. And then also we know as a result of all this that carry flag is also equal to 0. And then from that point, we just can, if we want to actually talk about what the hexadecimal result of this is, well, just take the result here and then just convert that back, right? Convert that back to hex. So AL in terms of hexadecimal would be the E and then 3, right? Since we have the 14 here for the first 4 bits, and then 3 for the second 4 bits. And then again, we also know that carry flag is equal to 0. So that would be the final result then of this. So again, whatever situation comes up, right, we can handle it in terms of interpreting the data here. Because what we're seeing is that even if the data is given in hex, that's okay. Just, convert it, either mentally or on paper. Do the shift at the binary level, however many times you need to go, whether it's 1 bit position, 2, 5, 10, whatever, and then just convert the final result back to hex. So all this leads to the conclusion that if the original value was 8D hex, and then we did an arithmetic right shift, 2-bit positions, then we're going to end up with E3. And it also worked out to where we had carry flag was 0. So also when you shift like that multiple times in one instruction, the value in the carry flag is always the last value that gets shifted out. So again, if you look at the intermediary steps here, there was a point where carry flag was 1 after the first shift, and then it was equal to 0 after the second shift, but it's the last shift that really matters, right? So since the last shift out had carry flag as 0, that's the actual value of the carry flag after, after doing this instruction here. So AL is equal to E3, carry flag in this case is equal to 0. Now, let's look at another example here, because we have been saying, right, that that also SHR and SAR are different. Let's do 4 here, because we can actually take a shortcut here in this case, really, 4. But so move AL, right, 8DH. But if we use SHR, that's doing, like we said before, a logical right shift, meaning that zeros, if you think about the data at the binary level, zeros are always going to be shifted in, as opposed to looking at the MSB bit. Now here, if we're going 4 times, well, certainly one thing you could do, here in this case is we could go step by step. But 4 also corresponds to the number of bits in a single hexadecimal symbol. So in effect, right, if we move, 8D hex into AL and then do a logical right shift by 4 bit positions, then we're shifting out, right, all the bits that make up the D, right? Because we're going in the right direction. We're saying to go 4 bit positions. So that means all 4 of the bits that make up the D are going to be shifted out one by one. But the end result is that all 4 of them are going to be shifted out. So really, in this case, if we have something like 4 as the shift amount, we can kind of take a little bit of a shortcut there, given that we know what's going to happen. So we know what's going to happen. We know that all 4 bits of the D are going to be pushed ultimately out of the number, and then furthermore, zeros are going to be pushed into the number since it's SHR, right? SHR always, right, pushes in a 0, whereas SAR, just like we saw with the example here, because this one was SAR preserves the sign. SHR does not preserve sign because it's intended really for unsigned, right? For example, unsigned division by powers of 2. So, but again, a little bit of a shortcut here is also recognizing that if you're going 4 times, well, that corresponds also to D, right? The number of bits that make up D, since we're going in this case in the right direction. So all 4 of those bits are going to be shifted out. At the same time, we know it's getting pushed in, right? We know that it's going to be really 4 zeros pushed in. So that gives us an idea of what the final result is going to look like, and for that matter, what the carry flag is going to be storing. So in a hexadecimal sense, right, since we know that we're shifting 4 times. We're shifting 4 times, and each time we're shifting in a 0 bit to the high end. So 4 zeros, which is 0 in hex. At the same time, we still have all 4 of the bits that make up the 8, because none of those were pushed out, right? So we have, for example, here, 0, 8 hex. And but also, what about the carry flag? So what's going to be the value of the carry flag in this case? Well, you could go step by step, but we can also infer that from thinking about everything that's being pushed out here. So in particular, remember, we're pushing out all 4 bits that make up the D are being pushed out. So you can take a moment, but think about what does that imply about the carry flag, right? The final value of the carry flag after doing all 4 of your bit position shifts. Because remember, the instruction here is going 4 times, but it's the final, right? The final bit that gets shifted out. That's what's going to finally be stored in the end in the carry flag. So we're shifting out all 4 bits that make up the D, but we can infer from that what that means in terms of the carry flag. So what's going to be that value of the carry flag? Well, we know that D, right? If you think about D, so in particular, we know that D in hex, D is 13. So D in hex is going to be this, right? 1101 or 13 is a binary number. But we're shifting out, right? We're shifting out all 4 of the bits. So the idea being, if you only shifted 1 time, then this one would be the final value of the carry flag. If you shifted 2 times, right, then the 0 would be the final value in the carry flag. Or if you shifted 3 times, then this one would be the final value in the carry flag. If you shift 4 times, then this one will be the final value in the carry flag. So remember, all 4 are shifted out, but the last one to get shifted out is going to be the final value in the carry flag. So now what that means is we also know that that carry flag is equal to 1. In particular, right, this one is what finally in the end ends up in the carry flag, right? Since we're shifting in the right direction, where the carry flag is the rightmost thing that's involved in the shifting process. The last thing that's shifted out is this MSB bit for the D, which, right, is going to be here. So again, that in this case, it worked out, to where it was easy to take a little bit of a shortcut, because, you could certainly convert this to binary and then go step by step 4 times. But the idea is that since the shift amount was 4, and 4 corresponds to the size of a hexadecimal symbol, we just took a little bit of a shortcut here by recognizing that, hey, well, we're actually just shifting out really all 4 bits of the D. So I'm going to lose the D, and the 8 is moving 1 hexadecimal position over, and where the 8 previously was, I'm going to have a 0, right? Because I'm shifting in 4 zeros each time. So again, it's just a little bit of a shortcut that we were able to take here. But that was the idea, is that the D is getting shifted out completely. The 8 is moving over. And then each time, right, if you think in terms of the binary level, you're shifting in 0 bits 4 times, and 4 zeros is 0 also in hex. So putting it all together in the end, we got 08 hex as far as the value in AL, and then carry flag was equal to 1, right? Since we, since we were shifting in the right direction. So the last, or the MSB bit from the D, is the final value in the end that ends up in the carry flag. So just a little bit of a shortcut that we were able to take there. Now, of course, I mean, you could try to do really any of these. If you want to do it mentally, you could. But the other approach was just to kind of do everything explicitly and go step by step by step by converting to binary and doing each individual shift one at a time, and then building up to the final result and then converting it. So there's, in general, different ways that we can try to tackle these problems. But again, here it worked out to where the shift amount was 4. And since that is also the size of a hexadecimal symbol, it was really just a matter of recognizing that the D is going to be completely shifted out. And then what you're going to end up left with is 08 along with 1. Along with 1 as the value, as the final value in the carry flag. Okay. And so that's the basic idea. And we're starting to see that, there's different potential practical usages of these shifts. So one thing we said is that you could, for example, analyze the individual bits in your number, and then with the help of the carry flag and the jump instructions related to the carry flag, you could, for example, go through each bit in the number, check if it's a 1 or a 0, and then that determines what happens next. So that's one example of things that we could do. But another example also were things like doing some basic multiplication by powers of 2, or either unsigned or signed division by powers of 2, where multiplications would correspond to left shifts, right? Moving the number up to higher powers of 2, right? And then division, either with signed or unsigned, would correspond to going in the right direction, where you're moving the bits right to lower powers of 2. So those were other potential usages of these instructions to do some basic division or multiplication by powers of 2, or analyzing the bits with the help of the carry flag. Okay, so any questions so far? So for example, some of the bits are being used to store the year, some of the bits are storing the month, some of the bits are storing the day, but they're all together here in register DX. And when we read through the program here, it talks about having this variable month in the data segment, and then the goal of the program is to move only the 4 bits for the month, meaning the bits that are labeled here, bits 5 through 8. Those 4 bits are for the month, and then the idea is that we want to move only those 4 bits into this month variable. Now, of course, month is a byte variable, so the actual value that we move in is going to be a byte-sized value with a total of 8 bits, but the idea is that really 4 bits are controlling the month. So the month is going to be a value between 1 through 12, and they're stored in those 4 bits. So the idea is that putting it all together here, right? So day, for example, that's actually 5 bits 0 to 4, and then month is 4 bits from 5 to 8. And then we have 7 bits, for example, for the year from from 9 to 15. But we're basically wanting to isolate the 4 bits for the month and have that control what's stored in the month variable. And so the bits here, meaning bits 5 through 8, are storing a value between 1 through 12. And the goal is for that to end up in the month variable. And so then the question's about, which of the options is going to be correct here. And so with this first option here, this one turns out to be the correct one. And so what we're doing is, again, we're isolating basically those 4 bits from dx, but we're also preserving the value in dx, right? So we're going to keep the original value of dx. So we started here by moving dx over to ax, and then we did a shift right on register ax by 5-bit positions. And the idea was that if you shift right 5 times, that is going to shift out the 5 bits that make up the day. Remember, this is in AX, so we're still not changing the original DX values. But we're shifting out in terms of AX, right? We're shifting out the 5 bits that make up the day, which means that now at the low end, right, at the lowest 4 bits of AX are going to be the 4 bits that make up the month. And, since we're using SHR here, it also means that in terms of AX, we shifted in 5 zeros on the high end, which are not really going to be used here, but we shifted out those 5 bits that make up the day. So now we have the 4 bits for the month now at the low end, right? The lowest 4 bits of AX. And now we can work from there. So the point of the shifting was to really, because remember the idea is you want to store the number between 1 through 12 in this month variable, right? So it was good to get that day shifted out, which now means the 4 bits for the month are at the low end, and now we can work from there. So shift out those 5 bits for the day, and then notice the next thing is one of the chapter 6 instructions, but we're doing an AND operation. But notice that we're saying and now we're talking about the AL, right? Just the AL part of AX, because that corresponds to, right, what we're dealing with. But and AL, and then the first 4 bits are zeros, the last 4 bits are ones. So what we're saying is that the month itself really only takes up 4 bits. The remaining bits aren't really used, but they need to be zeros, right? The upper 4 bits need to be zeros. So that way it's the lower 4 bits that are only contributing to the magnitude of the value in AL, because the next instruction here is just move whatever's in AL into month. But the idea is that after we've done the shift, now the lowest 4 bits are the month bits, and those 4 bits together are a number between 1 through 12 as a 4-bit binary number. But of course, I mean, when we think about actually moving this to the variable, I mean, we're still working at the byte level. So still have to think in terms of an 8-bit value that we're going to move. But the idea is that the 4 bits that make up the month, right, those are the low 4 bits. The upper 4 bits should all be zeros, right? Because if any of those bits were ones, then certainly you would have a big, a number that's bigger than 12. So make sure that those upper 4 bits of AL are 0. And then that way the month is controlled only by the lower 4 bits. So what we did here was, after shifting AX 5 times to the right to get the day bits out, and now the month bits are at the low end, now we say, well, I'm going to take the lowest 4 bits and I'm going to AND those with ones. Because when you AND with 1, you're going to have the original values, right? Because if a bit was 1 and then you AND it with 1, it's still going to be 1. If a particular bit in that 4-bit sequence was 0 and you AND it with 1, it's still going to be 0. At the same time, we force the upper 4 bits to all be 0. So that way they're not contributing to the magnitude of what we interpret as the month. So force the upper 4 bits to be zeros, keep the 4 bits for the month the same by making those ones, and then move that, right? Move all of AL into the month variable. So the end result of all that is now the month variable is going to correctly store a value between 1 through 12, depending upon what the month was originally set to in DX. So in this case, what we're doing here is we actually combined a little bit of chapter 6 also here into the mix as well. And again, the other options all have various issues. So some of them are trying to shift in the left direction, but we really want that the 4 bits for the months to be at the low end, since the value is strictly a value between 1 through 12. So in this case, we actually want to shift in the right direction, and then it's going to need to be and rather than or. If you think about the first two options here, it needs to be and, because we need to force the upper 4 bits to be zeros and then still preserve the lower 4 bits. So that's why this one's a problem. And then the other two options are also a problem because they're trying to go in the wrong direction, right? The other options are basically trying to shift out the year bits, but then we have the month at the high end, which is not really convenient because, you know, if you have the 4 bits for the month at the high end and you just leave it like that, well, then you have the 4 bits in the wrong bit positions, right? Because you're going to have numbers that are much larger, right, than 1 through 12. So we really want the month bits at the low end, right, not the high end. So we shift right. And then after shifting right, we follow that up with the and instruction to force the upper 4 bits to be 0 and then keep the lower 4 bits the same. And then once that's all done, just move all of AL into month. And now we have correctly moved that month value into the month variable that was defined in the data segment. So shifting to the left in this case is not going to do what we want. And then we also do need to do an and as opposed to or in this case after shifting to the right. So based on all that, then option A up here is the correct one. So shift right 5 times and with that bit sequence, and then move that into the month variable.